So message authentication codes, when we looked at hash functions, we saw that we use hash functions for authentication. Authenticate the source user. When we receive a message, we want to be sure that that message came from a particular source user, not someone pretending to be that user, so not someone performing a masquerade attack. And also to make sure that the message has not been modified along the way, which is data integrity. So authenticating the source and also providing data integrity. That's where we saw the examples of hash functions. We're going to look at another approach, message authentication codes. So very similar, provide the same sort of services, just a slightly different approach. In fact, before we go through Max, we'll go through the more generic approach of authentication. You're welcome to stay if you like. It's an interesting topic. Not so hard.
Yeah. It's so much fun.
Yeah. Let's look at the basics. Before we go into Max, look at the basics of message authentication, which we've mentioned many of these things before. Coming back to almost our first lecture, the different types of attacks that may occur and the mechanisms that we use to try to prevent those attacks. Disclosure of message, that is releasing the contents of a message, traffic analysis. We use encryption to try to prevent those attacks. If we don't want someone to see our message, we encrypt that message. Provide the service of confidentiality. What about masquerade attacks? Someone pretending to be someone else? Then we need message authentication to make sure that we can confirm who the message came from. If someone modifies the content, then again we need message authentication to make sure that when we receive a message, it has not been modified along the way. Provide the service of data integrity. Similar if someone modifies the content of the message, or similar attacks, a modification attack is modifying the sequence of messages sometimes. A source sends 2 messages. If the attacker can reorder those messages, sometimes they can perform some useful attack, even if the content of the message does not change. Maybe not the best example, but one example, the first message is you send increase the bank account, so it's sent from one bank computer system to another, increase the bank account of Steve by 20,000 baht, and then the second message is decrease the bank account by 5,000 baht. So if I originally have 1,000 baht in my bank, the first message says increase by 20, I go up to 21. The second message says decrease by 5, I go down to 16. So my balance is 16,000 baht. That's fine. If we reorder those messages, if the attacker can reorder those messages, what happens? My balance is originally 1,000 baht. If the attacker can get the second message to be sent first, which says decrease by 5,000, I'm currently 1,000. Decrease by 5,000, my account is minus 4,000. I have to pay a fee because my account is now in the negative. So there's an attack on me because I have to pay some extra fee because I've gone over the amount I'm allowed to have in my account, or I've gone under. I've become a negative amount. So a very simple example of if the attacker can reorder some messages, they can often or sometimes perform some useful attack from their perspective. Change the sequence of the messages, not just the content. And similar timing of messages. If you can delay messages sometimes, that can be useful from an attacker's perspective. To prevent these modification attacks, we need authentication. Non-repudiation, preventing someone from denying that they've done something in the past. Preventing a source from denying that they sent that message, or preventing a receiver from denying that they received the message. Then we can use digital signatures in that case. Where, remember, a digital signature, in practice, we take a message. To sign that message, we take a hash of that message and encrypt the hash value with the private key of the user, that's signing the message, which can be used to confirm that that message must have come from a particular user. That user has signed it, and therefore at a later stage we can confirm, okay, that user signed it, they must agree that they sent that message. So we've seen examples of all of these. Encryption, the first half of the semester. We've seen last week authentication, and also we introduced digital signatures. How do we do message authentication and also digital signatures, because they're very similar? There are two different parts. There's this mathematical function that produces this message digest, the hash value, or more generally the authenticator. That is, we take a message and we do perform some operation, some function on that message, and we get some output, produce some authenticator, some information we can use to authenticate. And then there's some protocol to allow the receiver to verify the authenticator. We saw some examples last week of those diagrams of how we apply some hash function, and that the receiver can compare the calculated hash against the received hash to verify if everything's okay. That's the general things that we need for authentication. There are different types of authentication functions. Last week we saw the hash function as one type. Have a message, calculate the hash of that message, send the hash value. And the receiver can compare the calculated hash value against the received hash value and check. So that's one approach. Another approach, and we touched upon that last week as well, is to use message encryption. Just use symmetric key encryption to encrypt a message. If we decrypt and the received plaintext looks correct, then it gives us confidence that it came from the right person. If we decrypt something with the expected key and the plaintext looks like garbage, that is random characters, then that looks like that we've used the wrong key or the message has been modified. So we can use encryption to perform authentication. And the third approach, which we'll touch upon today, is using what's called message authentication codes, MACs. Not medium access control. Now we have MACs in security of message authentication codes. Let's look at those general types. So how can we... So last week we looked at how to do authentication with hash functions. We're going to look at how to do authentication with message authentication codes, but let's go back and show and remind you how we do authentication using encryption only. Here's some examples. This is using symmetric key encryption to perform authentication. We take our message, encrypt using a symmetric key algorithm such as triple DES, AES, using a shared secret key K, send the ciphertext across the network. The receiver tries to decrypt with the corresponding shared secret key K using the same algorithm, triple DES for example, and they get some output plaintext, some message. This of course provides confidentiality. Only B and A can recover the plaintext. Only they can see the plaintext. It can be used to provide source authentication because if it successfully decrypts with key K, so user B that receives it successfully decrypts with key K, then B assumes that it must have came from user A because only A and B know key K. It's a shared secret between two users only. So that's authenticating the source. If it successfully decrypts, it must have come from the other person who has that secret key. And authenticating the content, the data, making sure nothing has changed. Because if it successfully decrypts, then that means that the data has not been modified along the way. Because if the attacker modified the ciphertext, it would not successfully decrypt. So we've authenticated the source and the data. From the services, we've provided the authentication service and data integrity service. The last two rely on the assumption that the entity decrypting can recognize the correct plaintext. That is, I said, if it successfully decrypts, how do we know something successfully decrypts? Well, if the plaintext that we get from the decryption has some structure that we can recognize. Go away. Go away.
What is solar?
Solar is an access point, wireless LAN access point downstairs. And it uses WPA encryption and authentication. But that's not the point of it being there. Here's an example, a simple example to show that we need to be able to recognize the plaintext to do authentication. In this first example, B receives some ciphertext. They think it's from A, and they've shared a secret key K with A. Here's the ciphertext. B, or you, B, you decrypt that with the key that you share with user A, and you get this plaintext. Security and cryptography is fun. Do you think that this message came from A? If I'm user A and you user B, do you think this message came from me? Are you confident it came from me? Yes. The plaintext has some structure that you recognize, so you would make the assumption that, well, this is the correct plaintext. It is successfully decrypted. Because if you took some ciphertext and decrypted with some key K, and if you get some English phrase, it's highly likely that you've decrypted with the correct key, the correct ciphertext. Because if you decrypt with the wrong key or the wrong ciphertext, it's highly likely you'll get random characters here which will make no sense. So this has some structure, so we assume that it was sent by A. That is, it must have been encrypted with the key K, and only user A has key K. And the ciphertext is the same as what was sent. That is, there's nothing being modified along the way because, again, it successfully decrypts. So if the plaintext that we get from decrypting has some structure which we recognize, we assume it came from the source A and it was not modified along the way. That's easy. You can recognize the structure there. What about this example? You, a user B, you receive this ciphertext, Q, E, F, and so on. You decrypt. You think it came from user A. You decrypt with a key from user A, and you get this plaintext. What's your assumption now? What do you do? Do you think it came from A, or do you think maybe an attacker has modified this? Yeah, you said modified. Why?
Maybe they don't know English.
Is it in a different language? Possibly. So we need to be able to recognize the language if it's in plain text. We're not sure. We don't immediately see some structure here. So somehow we need to be able to recognize, is this correct plain text? If it was in a different language, then we'd need to understand that language, if it's just text. What if it was a binary image? Not some plain text, but some JPEG image which we sent. So the question is now, from this plain text, can we recognize if this is correct or not? I cannot from this case. Let's say what was sent was not some text message, but some JPEG, some image, which we really think is a sequence of bits to represent the pixels in that image. So the ciphertext you received is this binary sequence, or this is a part of it. You decrypt and you get this binary sequence. Can you see whether this is correct or not? Again, it's hard to recognise any structure there. We need to be able to recognise the structure in the decrypted plaintext to be able to perform authentication. That's the point here. In example 1, we assumed the message was English. So the plaintext had the expected structure, and therefore we assumed, because the plaintext had the structure of some English phrase, so therefore we assumed the plaintext was correct. We had authentication. In example 2, if we assume the message is in English, the plaintext we expect to receive is in English, then in that case we would make the assumption, okay, the plaintext we got had no structure that we recognised. So in example 2, we would have assumed that something went wrong. Because we decrypted, we got some random set of characters, then we would have assumed that either A did not send it, or someone along the way modified the ciphertext. That is a problem with authentication. And maybe you can see down the bottom, is there another line? Maybe not. In example 3, we had binary data, say image or some compressed file, text that was compressed. Then there was no way to know whether it was correct or not. If we know that the structure is some English text, then there's usually a way to know whether it's correct or not by looking at the message. If it's binary, not so simple. So, we need to have some structure in the plaintext. If we don't have some structure that we can automatically recognise, then we can add some structure to that plaintext, such that the receiver, when they decrypt, can recognise some structure. So how do we recognise correct plaintext? If we're looking at the English, then the valid, or any language, the valid plaintexts should be a small subset of all possible messages, such that if we use the wrong key, or if the ciphertext has been modified, when we decrypt, we get some value which is not a valid plaintext. Just go back. If we receive this ciphertext, decrypt with key K, and got this plaintext, security and crypto is fun, then if the attacker did modify the message, that is, this ciphertext has been modified by the attacker, and by chance we got this English phrase, then our authentication would not work. So this authentication being successful relies on the fact that when we decrypt some ciphertext, getting a valid plaintext is highly unlikely if something is different in the ciphertext or the key is different. That is, the set of possible valid plaintext is very small compared to the possible set of all messages. That's what we require. And that's the case in English. In English, we can take any of the 26 characters and rearrange them in any way we like. So if a message of n characters, we have 26 to the power of n possible combinations of messages, the entire subset, the entire set of messages. Only a small subset of them are valid English phrases. You take n equal 4 as a simple example. You rearrange you write down all the possible values of 4 letters in length, and there are 26 to the power of 4 possible values, all up to z, 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 z. Of those 26 to the power of 4 possible arrangements of 4 letters, only some of them will make words that you are English in the English dictionary, or make short phrases. So that's true with most languages, that of all possible arrangements, only some of them make sense. And that's why it's easy normally to automatically detect if the plaintext is correct if it's in some known language. But what about if we have binary data or if we have compressed data? Then we need some way to automatically detect the structure. And one way to do that is to add structure to the plaintext to make it easier. Add an error detecting code or a frame check sequence. It was mentioned last week, similar to a hash function. Hash function using an error detecting code or a frame check sequence like CRC adds structure to the message so that if we decrypt, if we get the expected structure, it's okay. If we don't get the expected structure, then we assume something's gone wrong. When we use network communications, packets that we send have some structure. We send a TCP packet. The header field has some expected structure. If we encrypt that TCP packet, and at the receiver we decrypt, if we don't get the expected structure in the header, then we can assume something's gone wrong. So if we don't have structure that we can automatically detect in a message, we can usually easily add structure. Using some frame check sequence, add something to the end, as an example here, and encrypt that frame check sequence, and the receiver verifies that message. Or add, when we send a network packet, the header structure is used at the receiver to detect if something's gone wrong. Because if I encrypt a TCP segment, and then at the receiver I decrypt it, we'd expect that the structure would be recognized by the receiver. The source and port number should be similar to the previous that the application set up. The acknowledgement and sequence numbers have some structure, and so on. So in practice, we can use encryption to provide authentication so long as the plaintext has some recognizable structure. We can use hash functions, encryption, and the third approach is we can use message authentication codes. We can use public key encryption, as same as symmetric key encryption, encrypt using a public key. We can use digital signatures to provide authentication, and we can combine them. If we want both authentication and confidentiality, we can combine encryption for confidentiality as well as for signatures. We've mentioned this in the previous topic. Let's look and move on to the third approach, using message authentication codes. And it's very similar to hash functions. A message authentication code, what we do is we take our message and attach a small fixed size block of data, which is called a message authentication code, a MAC, or a cryptographic checksum. It's a checksum, like a CRC, an a parity bit checksum, but the algorithm is normally designed specifically for cryptographic purposes. And what we do is we take some message, apply our MAC function on that message using some secret key K, and we get some small output, small fixed size output, either the message authentication code, sometimes called a tag, T. So the input to our MAC function is a message, M, and a shared secret key of some length, some K bits. And the output is a message authentication code. Sometimes you'll hear me say a MAC code, but that's not correct. It's a message authentication code, or a MAC, or sometimes called a tag of some fixed size, usually small. Similar to our hash function, recall our hash function. In general, the hash of a message and the output is some hash value, where the hash value is small, fixed size. A MAC function will take a different function, a MAC, of some message and produce some small, fixed size output. Here we also have a shared secret key. Our hash function did not use a secret key. A MAC function does. And they are very similar, and sometimes a MAC function, this function here, would be called a keyed hash function. It's a hash function, same purpose, but we also use a key, a secret key. It's similar to encryption. When we encrypt something using symmetric key encryption, we would write it like this. Ciphertext equals the encryption of some message, the plaintext, with some shared secret key, K. Here, some message, apply the MAC function with some shared secret key, K, and we get some tag as the output. So there's similarities with symmetric key encryption. And there's similarities with hash functions, except now we have a key, whereas a hash function does not. Similar to encryption, but does not need to be reversible. With encryption, we need a corresponding algorithm that takes the ciphertext and the same key, and it must get the same M as output. We need to be able to decrypt. With a MAC function, we don't need to be able to decrypt. So with encryption, we need to be able to do decrypt the ciphertext with key K to get the message. That's required for encryption and decryption. That's not required for our MAC function. That generally makes it easier to design MAC functions that are secure. That is, we don't need a function that does this. So on function f, take the tag, the output, and apply the key and get the message. That's not required and not desired. So in general, designing these algorithms, these functions, is easier for a MAC function than an encryption algorithm. Let's look at some uses of a MAC function. 3 different cases here. First one, take a message. In these diagrams, the C here is our MAC function. So take the message, apply our function C. C is the MAC function. Using some shared secret key K, we get the message authentication code or the tag as an output, concatenate that tag with the message, send them across the network. The receiver takes the message, the received message, applies the same MAC function C with the same shared secret key K, and they get a calculated value of the tag. If that matches the received value, everything's okay. If it doesn't match, then the receiver assumes either an attacker has modified the message or has modified the tag, the MAC value. That is, it provides integrity, data integrity, and authentication of the source user. And you can check that the same way that we check the hash function. How does a hash function provide authentication? Check. What if the attacker modifies M, but not the tag? If they change M, then the receiver, when they calculate using the secret key K of some modified M, they'll get some tag which should be different from the received tag. If they're different, then something's gone wrong. That will lead us to one of the properties, similar to our hash function properties that are required. Finding 2 messages with the same tag using a key should be difficult. We can do that, but combine it with encryption as well. And that's what the second 2 diagrams here do. The middle diagram, takes a message, applies our MAC function with some shared secret key, K1, gets the output tag, and then concatenates with the message and encrypts everything. So in the second diagram, let's say when we apply our MAC function, it's denoted as C in these diagrams. I might write it simpler to make it clearer, MAC. If we apply the MAC function on some message with key K1, we get some output, let's call it a tag, T1. And then we concatenate that tag with the message and encrypt everything. Encrypt using a symmetric key cipher, using a different key, K2. We encrypt the message combined with a tag, the output here, with a different key, K2. Encrypt the MAC, the message combined with the MAC of that message. So this provides confidentiality as well as authentication because we've encrypted the message. And the second one is similar, but note that the ordering is different. Take the message, encrypt the message using some symmetric key cipher with key K2, and then take the ciphertext as output, calculate the MAC on that ciphertext, and send the ciphertext combined with the MAC of the ciphertext. In the second diagram here, we encrypt the plain text and the MAC of the plain text. In the third diagram, we send the ciphertext and a MAC of the ciphertext. Providing similar services. Any differences? They provide the same services. One is applying the MAC on the ciphertext, the other is applying the MAC on the plain text. There's some differences in terms of the ease it is to perform some operations at the receiver, performance and functionality wise. There are also some differences that we do not have time to explain of some chosen ciphertext attacks are easier to prevent using the third approach compared to the second approach. But one difference that we can illustrate and easily see here, at the receiver in the third case, we take the received ciphertext and the MAC of that ciphertext, and we can check if anything's gone wrong. That is, take the ciphertext, check using our MAC if the received ciphertext has been modified. That is, we do the authentication first. In the second approach, the second diagram here, we must decrypt the message first. In terms of performance, decrypting normally takes more effort than applying a MAC. Applying a MAC is much faster than decrypting the entire message. So, this can be useful, this third diagram here can be useful for preventing the impact of, or reducing the impact of denial of service attacks. If an attacker sends many modified messages to the receiver, in approach 2 here, the receiver needs to decrypt the entire message and then check if it's correct or not. And they'll determine that it's incorrect message and discard it. Decrypting every message they receive takes up a lot of resources on the receiver computer. In the third approach, we don't decrypt the message, we just check the MAC first. If we check the MAC first and discover immediately that there's something wrong, we discard the message without decrypting. So imagine I'm the receiver, I receive thousands of these incorrect messages sent from an attacker. In the second approach, I have to decrypt everyone. And then I check and I find it's wrong and I discard it. I use up a lot of resources decrypting that message. In the third approach, I receive thousands of messages. When I receive one, I quickly calculate the MAC, find that it's wrong, discard the message before I have to decrypt. Because calculating the MAC is faster than decrypting, and significantly faster in many cases, then the third approach uses less resources. So there are some advantages and disadvantages of these, the order in which we apply the MAC and do the encryption. One advantage of the third approach is to reduce denial of service attacks. Again, you can go through and look what happens if an attacker modifies the message in each of these, or modifies the MAC. You'll find that if they modify the message, the receiver will detect that modification because of the MAC function, so long as the attacker cannot choose a modified message which has the same tag, same message authentication code as the original message. And also, so long as the attacker does not know the secret key. The attacker must not know the secret key. So the same concepts apply as in hash functions, except now we have a secret key involved. We'll look briefly at the security. How do we measure the security of MACs? And then look at a couple of example MAC algorithms. Remember, with our hash algorithms, hash functions, we had three properties: one-way property, weak collision resistance, strong collision resistance. They had some different names as well. Which one was easier for the attacker of those three properties?
Easier is one no and five other one.
And I don't know if that's correct. Which properties? Strong collision resistance, weak collision resistance, or one-way property? Which one's easier for the attacker to defeat? Strong collision resistance. Strong collision resistance, the property requires it must be hard to find any pair of messages that produce the same hash value. It's easier to find any pair of messages than it is to find a message with the same hash as a particular message. And approximately the level of effort depends upon, for the one-way property and weak collision resistance, it depends upon the length of the hash. If the hash is m bits, it's 2 to the power of m, a brute force attack. With strong collision resistance, it's about 2 to the power of m over 2. So much easier. Similar with MAC functions. And on this slide there are two typos. The objective of the attacker is to find, if they know the MAC function, they don't know the key, find a valid MAC code for some given message X. Instead of for, it should be find. Find some MAC code that's valid for some given message X, but they don't know the key. And we can state a property of the MAC function. Given one or more text MAC pairs, so pairs of the message and the MAC of that message, if the attacker knows some pairs, usually more than one, it should be computationally infeasible for the attacker to compute, not computer, to compute any text MAC pair for some different value of text from different message M. So if the attacker knows some values, If the attacker knows some message M1 and some tag T1, where T1 was calculated from the MAC using some key of M1, so if this pair of message or text and tag is known by the attacker, it should be hard for the attacker to take some other message, M2, and find T2. That's what the property states. It should be hard for the attacker to find the tag of this message, even if they know the pairs of other messages, because they don't know the key. The normal user knows the key. They can easily calculate T2. It's just the MAC of M2 using the key. If we don't know the key, it should be hard to find T2, even if we have previous pairs which were obtained using that key. If the attacker can find a tag without knowing the key, then they can perform attacks on the authentication and integrity of messages. What approach can the attacker take? A brute force attack. Try to find the key. If they find the key, then they have broken the system, because the key must be kept secret. How do you find the key? Try all possible keys. Let's say the attacker knows this pair from previous communications, that there's been a message in the past, M1, that was sent and the corresponding tag was sent. We don't know what K was. So what the attacker does is to try all possible values of the key and see which... Try all possible values of key on this message M1 and see which one produces the tag T1. That is, with key 0, calculate the MAC of M1, which is known. Sorry, I wrote it the wrong order. The MAC using key K0 of M1, we get some output value, T10, and then use the next key, a brute force on the keys. And so on, for all possible keys. And with a key length of k bits, we need to try 2 to the power of k keys. I should have started at 1. The last key, 2 to the k minus 1. So try many keys, calculate the MAC using that last key on the same message M1 and get some tag 1. If k was 4, we'd have 16 possible keys. We'd have to calculate 16 possible tags. On that same message M1, some of them will match this tag. And if they do, they give us information about what the key was used. Let's say this tag and this matches the one that we know. Then that indicates that the possible key that the original user used was K1. But our tags are usually small and fixed size, where our message may be large. So we may have multiple tags that match this tag. What do we do if we have that case? Let's say I have 3 tags which are the same as this known one. Then I have 3 possible keys. What do I do as the attacker? You did similar to this in the meet in the middle attack on double des. If you find a set of possible keys, then you try with another pair of known message and tags. If you also know M2 and T2, where T2 was obtained using the same key K, if you find a set of possible keys, you check them with the second pair and they should indicate the correct key. So we've done a brute force attack on the keys, tried all possible keys. With a k-bit key, there are 2 to the power of k possible keys. So the number of attempts we need is 2 to the power of k. Even if we find multiple tags and we need to check again, usually it's much smaller number of checks that we need to do in the second and the third case. So the effort is approximately equivalent to 2 to the power of k. Longer the key, the harder a brute force attack is to find the key. So one measure of the strength of a MAC function is the length of the key. The other way to do a brute force attack on a MAC is to try to find, for some given value of your message, find the tag without knowing the key K. And it's similar to breaking the one-way property or weak collision resistance in a hash function. In the hash function, one of the challenges for the attacker was given some message, given some hash value, find the original message. Same problem we have here. And that depends upon the length of the MAC value. In the hash function, it depends upon the length of the hash value. If we have an n-bit MAC value, then the effort is approximately 2 to the power of n. So there are 2 approaches to do a brute force attack on a MAC function. Find the key, or do the inverse to find some message without knowing the key. The first approach depends upon the length of the key. The second approach depends upon the length of the MAC value. So we measure the strength of a MAC function based upon the minimum of those 2. That is, the attacker takes the easiest approach. If we have a MAC function with a 4-bit key and it produces a 6-bit MAC value as an output, that is, we take the function with some input key of 4 bits in length and produce a 6-bit value, then what's a brute force attack going to take? How many attempts in worst case? What are you going to attack, the key or the MAC value? You take the easiest approach and attack the key. That is, if a 4-bit key, trying to find the key, we need to attempt with all possible keys. There are 2 to the power of 4 attempts that are needed. With a 6-bit MAC value, using this approach, there are 2 to the power of 6 attempts needed to find it to directly break on the MAC value. That is, with these 64 attempts. So the attacker would try to do the brute force attack on the key in this case, and their number of attempts depends upon the key, 2 to the power of 4 or 16. If the key was 10 bits and the MAC value was 6 bits, then they would attack based upon the MAC value. They take the simplest approach. And that's why we say the effort to break the MAC is the minimum of the length of the key and, well, we choose an attack depending upon the minimum of the length of the key and the length of the MAC value. And the amount of effort is a minimum of 2 to the power of k and 2 to the power of n. K is the key length, n is the MAC value length. In the hash function, the avenue of the attack was only on the hash value. It depended upon the length of the hash value, the effort needed to break it. two options to choose from in terms of security. Which is better, a 20-bit hash function or a MAC function that uses a 20-bit MAC and a 15-bit key? From a brute force attack perspective. Okay, let's look at the MAC function because we have the answer here in terms of the amount of effort needed. If we want to apply a brute force attack on the MAC function, looking directly at the MAC value, it depends upon the length of the MAC. We would need 2 to the power of 20 attempts. But if we apply the brute force attack on the key and try and guess the key, we'd need 2 to the power of 15 attempts. So that's, as the attackers, from the attacker's perspective, would try to break the key because that's less attempts. How do we measure the strength of the hash function? How much effort required to apply a brute force attack on the hash function? Can you remember? Sorry? Okay, it depends upon what property we require of the hash function. If we recall those 3 properties, one way, weak collision resistance, and strong collision resistance, and they had different names, the collision resistance, pre-image resistance, and second pre-image resistance. These two are approximately equal. That is, a brute force attack, you use the same approach. And the number of attempts depends directly on the length of the hash value, 2 to the power of n, where n is the length of the hash value. If you want to break any of these 2 properties, then it would take you approximately 2 to the power of 20 attempts. But the strong collision resistance property is easier for the attacker, and the amount of effort is approximately equal to 2 to the power of n divided by 2 to the power of 10. 2 to the power of 20 divided by 2 is the amount of effort needed to break the strong collision resistance property. So which one's better? If we require strong collision resistance on this hash function, then from the attacker's perspective, it's easier to break the hash function. If we didn't require strong collision resistance, as the user's perspective, then from the attacker's perspective, it would be easier to break the MAC function. It would require 2 to the 15 attempts. So we can approximately compare the strength of different MAC and hash functions depending upon the length of their keys and the MAC values and the hash values. In a moment, we'll go through quickly several examples of MAC functions. Any questions before we move on to that? Then we'll finish this topic and move on to the next one. We're not going into detail of how the attacks perform because most of it's similar to hash functions. If you look at what happens if the attacker modifies something, it's the same as what we saw last week with the hash functions, that it should be detected so long as they don't know the key or they can't find some other message with the same MAC value. That was about brute force attacks. What about using more knowledge of the algorithm to attack the algorithms? Cryptanalysis. There are many different MAC algorithms, and there are some specific attacks against some of those algorithms, but generally, and similar to hash functions, they are considered secure in that these other attacks are not much better than a brute force attack. If you recall or look back to the lecture notes, we said in the hash, was it SHA or MD5, that there was some attack that brings the effort down to 2 to the power of 64. Or was it 2 to the power of 60? Brute force attack, 2 to the power of 64. Some well-designed attack took 2 to the power of 60. Not much difference. It's 16 times faster, but 1,000 years compared to 1,000 divided by 16 years is still quite secure for most applications. So special attacks against these algorithms exist, but they're not much better than brute force attacks. So they're generally considered secure. Most of the current algorithms recommended. Let's just list some ways or some MAC algorithms. So there are some MAC algorithms that are based upon symmetric key encryption ciphers. Data authentication algorithm is based upon DES. So it uses DES to calculate a MAC value. And there's others, cipher-based MAC, which is basically a mode of operation. Remember our modes of operation, counter, CBC and so on. We can use them, or similar modes of operation, to produce a MAC value. Some of the names listed here, or the acronyms are listed there. Here's an example of DAA, the data authentication. Is that what it's called? Data authentication algorithm. And we see it's similar to our modes of operation. Take some value, a secret key, and apply the DES algorithm on that, get some output, feed that output into the next stage, XOR, keep doing that. This is our input message, our data, D. So we take our input message, break it into blocks, 64 bits here, data block 1, data block 2, data block N, apply some combination of those, and the final output here, we take a selection of bits to be our MAC value. So that's it. We take either, if we want a 64-bit MAC value, we take everything here. If we want a 16-bit MAC value, we could take the first 16 bits. And that's a MAC of our data or message on input using some shared secret key K. So really it's applying our modes of operation using our existing ciphers. And that's what the others do as well, but in different manners, and they have different advantages. This is CMAC. It takes the output for the encryption, K of K bits, and it does, what do we do? We have an XOR here with a K as well, and we take the most significant bits of a particular length to get our tag as the output. We're not going to go through any of these, and this is if it's a different length message. That's not so important. The point is that we can use many of our existing ciphers, symmetric key ciphers, to produce a MAC value. The other approach, which is quite common now, is to use hash functions to produce a MAC value. Our hash function, take a hash of a message, produce a fixed length hash value. MAC function, take a MAC of a message with some input key, produce a fixed length output. Hash functions like MD5 and SHA have been designed and used for a long time. There's a lot of software to use them. They're well known. So use those same hash functions, but also use a key to make it a MAC function. And that's what HMAC does. Turns a hash function into a MAC function. Turns MD5 into a MAC function. Because MD5, SHA, these existing hash functions are well known. There's software libraries available to implement them quickly compared to DES, triple DES and so on, which are quite slow to implement. So they're widely available, therefore it makes sense to make use of them. The basic way HMAC works is you choose some key, do some XOR operation on some fixed value, OPAD, which is just some sequence of bits which is defined and always the same. do it on an iPad, and this was around much before Apple created some tablet. So this is the original iPad, which is a sequence of bits, XOR with the key, take the hash of that. So we have we have key XORed with the constant, concatenated with some hash value, concatenated with our message, hash all of that, and we get our MAC value as the output. So it's a way to take a message, use a hash algorithm, and also use a key to get a MAC value as the output. And the security of that depends upon the strength of the hash function. So if you have a strong hash function, like SHA, then your output MAC value is considered strong. So that's commonly used as well today. And that has quickly gone through how message authentication codes can be used for authentication. So remember, for authentication we have three approaches: MACs, hash, and encryption. Because encryption on its own also can be used to do authentication, so long as we can recognize the structure in the message when we decrypt. Let's move on to a new topic. What's the next topic? Key management, key distribution. That is, we have public and private keys, we have shared secret keys. How do we get them to other people? How do we distribute them in a secure manner? But last week there were some questions about passwords, and there was a mention about PHP or programming languages. We can, when we save a password, we don't just save the password, we save a hash of the password. So we're going to skip key management and come back to that later and go onto the other topic of authentication and passwords. Since we're still on authentication, let's move to this topic. User authentication and passwords. We'll come back to key management after this one. This one's short, interesting, and something we can see some examples for. So we're still talking about authentication, but we're going to focus on how we use passwords for authentication, in particular authenticating users. So not necessarily authenticating computers, but authenticating when a user is involved in the system. Here's a quote from one of the recommended textbooks, or one of the textbooks that is an alternative to the Stallings textbook. Humans are also large, expensive to maintain, difficult to manage, and they pollute the environment. It is astonishing that these devices, humans, continue to be manufactured and deployed. But they are sufficiently pervasive, they are around everywhere, that we must design our protocols around their limitations. So in terms of security, humans cause problems. If we didn't have humans to design secure protocols, life would be much easier. But we need to design systems to work for humans. And the limitations we'll see in a moment. Compared to a computer, a human is limited in terms of, say, the number of operations that they can perform in their brain, what they can remember, and that has an impact on how do we design security mechanisms, especially authentication. For example, when we use computer-to-computer authentication, two computers are communicating. The computers can store keys in memory, can remember those keys, they're stored in memory. The keys can be long. A computer can store a 128-bit key in memory. Can you? If I give you a random 128-bit value, do you remember it? Can you remember it and tell me tomorrow? Mobile phone numbers, 10 digits, maybe. 128 bits, getting harder, especially random. So humans have this weakness. A computer can calculate the DES, apply a single DES operation in a matter of microseconds. How long would it take you in the final exam if I say calculate or encrypt this block of 64 bits with the real DES? Go through on a piece of paper and calculate. It would take you hours. Okay, so computers can perform calculations much faster than humans. So we need to design authentication mechanisms that don't require storage of long keys and don't require fast, complex calculations, because humans cannot do that. So that's why we need special methods for authenticating humans, for people. What's the basic things that we can use to authenticate people? Well, what you know, what you have, or what you are. What you know is some knowledge that you have, like a password, a passphrase, or a personal identifier, a PIN, personal identifier number. So you know how these are used. You get access to some system if you can tell that system some value that you've registered with it, a password or a PIN. So that's based upon what you know. The system authenticates you based on what you know. If you tell someone else that and they know that password, then the system will also authenticate them. So it's just based upon what you know, what you have in your memory. Another thing is what you have in general. If you have a key, you can come into the building. The building authenticates you based on you having the correct key. We can also apply that to security systems. We can have keys stored on USB disks. Take your USB and store a large, secure 256-bit random key. I don't have to remember it. It's stored on my USB disk. When I plug it into the computer system, the system checks that key and authenticates me. So that's based on what I have. Physical keys, an ATM card, ID cards, and other forms of authenticating based on what you have. Of course, if someone else gets a hold of one of these items, then they can also access the system. If someone gets my keys, they can get into my office. And what you are, based on characteristics of the human body, normally, based on your voice, based on fingerprints, eye scanners. So they're the main ways that we can authenticate people. In this topic, we're going to focus just on passwords, which, what you know, passwords, and also applies to passphrase and PINs. We're not going to focus on the physical aspects, and in fact, all of this course we don't look at physical aspects of security, and the biological aspects of security, biosecurity, we're not focusing on. But there are other ways to authenticate humans, and we can combine them. You need a card to swipe, you then enter a PIN, and then it scans your eyes. So you can add extra strength by combining them. We have fingerprint scanners on some of our rooms, so they're forms for authentication instead of needing a key to get in. Some of the labs in here have fingerprint scanners. They have different advantages and disadvantages. Let's look just at passwords, because you use them as programmers a lot. You need to manage them. What is a password? Well, we think of it as a combination of characters available from some input device, usually a keyboard or a keypad. A password on a mobile phone may be different than on a computer. The set of characters that are allowed may be different, depending upon what characters we can input from the input device. A password should be secure and easy to use, okay? By secure, it means that it authenticates the correct person. Only the person who is intended to access the system can access the system. easy to use, that that user is not inconvenienced when they need to supply that password. What's a passphrase? Well, simplest definition, a password, but allows spaces normally, usually longer than a password. But we can treat them the same, just a different set of characters available and different length. Some software will allow passwords only, just a word with no spaces, and have limits on the length. Some now will allow phrases, which have spaces and a different set of characters and a larger length usually, or require spaces and larger lengths. What's the problem with passwords? What can an attacker do to get access to a system when they're not supposed to? Well, some simple things. When you type in a password, when you're entering the system, the attacker can look over your shoulder and see what you type in. So everyone's in the lab and you log into your Facebook homepage, I'm just standing there behind you and I just watch the keys that you type in. I can easily discover your password in that way. Of course, that requires physical presence to do that. Or maybe not. Maybe I install some software on your computer that reads every key that you press, a keylogger. So all it does is that software, every time you press a key, it records the key that you pressed, takes a log of all that, and every day it sends me that log. I can analyze that log and look for patterns that look like passwords. That is, here's a pattern that is your username. Okay, it's likely that the next keys pressed will be your password. So in that case, I can see the password when it's being used without physical access, or without physically being there. Of course, when you supply a password to a system, the system checks whether the password you supplied matches a pre-registered password. We'll explain how that works in detail shortly. But if it checks against some pre-registered password, then that password that you originally registered must be stored on the computer system somewhere, in a file, in a database. If the attacker can get access to that file or database, then they can potentially get access to your password. So if the attacker can read the file where the computer system stores the password, they can access the password. Your password may be easy to guess because of limitations of lengths of passwords and structures of passwords. It may be easy to guess a password. We'll talk about how to measure that guessability of a password. And related to that, easy to guess, I may be able to guess someone's password based on their name, based on their date of birth, based on their where they live and different characteristics about them. Or I may apply a brute force attack. If I know a system has a maximum password length of 6 characters, just try all combinations of 6 characters. Some brute force attack. We say that that's crackable, or that attack is performed offline, in that it's not something I can normally do by going to your computer and trying all possible attempts. It's something that we need to, in practice, if I have some encrypted form of your password, I could try some brute force attack and try and guess that password. We'll see how that's performed shortly. Your password might be secure. So another problem with passwords is that you may have a very long password, random 128-bit characters, 128-bit password, but it may make the system too inconvenient to use, and therefore you may not use the system, which of course the system is still secure, but it's not serving its intended purpose. Or you may do other things like write down the password and make that strong password insecure by letting others see it. Many problems with passwords, but we must deal with them because that's the main way that users, humans, provide authentication to computer systems. Let's look at how passwords are used. Usually a user is identified by some unique value, like a username. That username is normally public. It's not kept secret. You all have usernames to the IT server. It's you followed by your ID. Anyone can usually guess that. Okay? They know, okay, so if someone in some other country wants to break into the IT server, it's usually easier to discover your username. They know that they work out that SIT is using this combination of you followed by an ID, then they just need to find your ID. Well, it's not so hard to find some user's ID. So a username is normally considered public. It's not kept secret. So a user is identified by, and it needs to be a unique value. And the secret is the password. And the user usually selects the password. Sometimes it's given to them. The system that we're trying to access, that is going to perform the authentication, stores that username and the password that you select in some file or database. And now for the user to access the system, they submit their username and password to the system via some protocol perhaps, or via some login mechanism. They submit their supplied username and password. The system compares the submitted values to the stored values. The stored values are what's created when the user is initially registered with the system. If they match, the user is authenticated. If they don't match, the user is not allowed in. Maybe they get another attempt. The issues that arise when we use this, what is a good password that a user should select, a strong password? How to store the passwords on the system such that it makes it harder for the attackers to get access to those passwords? How do you submit the passwords such that it's hard for the attacker to find them? And how to respond if there's no match? We'll talk about what is a good password. We'll look at the measurements of password. How do we store passwords on a system? A shadow file. What do you mean? That's the name of some file. What do you think that stores? Encrypt of what?
Of your password.
Encrypt the password on the system. Let's see how that works. That is, if I store on my computer system a set of all your passwords, if someone can get access to that computer system, some other means, then they see all of your passwords. That could be considered insecure. Well, let's store on the system a set of passwords but encrypted with DES, for example. How do we do that? Or alternatively, let's instead of considering a system, you took database systems last semester, you create a database for a website, and in that database you're going to allow users to register to that website, and therefore you'll store the set of users and their passwords in some database. Let's look at how we can store this information. User 1, user 2, user 3, and so on. So you have a database, you store the username and the corresponding password. For each user. So you create a database, store the username and the password. When someone accesses your website, you give them a prompt where they type in their username, they type in their password. Using HTTP, it sends that to your web server, which then checks in the database, does the supplied username and password match the stored ones? If so, then they are allowed access to the website. If not, they are not allowed. First, concentrating on how we store the passwords. If we store the passwords in their clear form, that is, we store the passwords as is, then the problem arises, I am the database administrator. Okay? I can access the database because I created it. Now, if we store the passwords in the database, I can see everyone's password. that can be bad from a security perspective, because you are a user in the system, everyone's a user, you supplied a password, it turns out your password's the same password you use for Facebook and your bank account. I've now discovered the password not only for the website I created, which doesn't matter if I get your password because I can do anything as the administrator, but if you use the same password for this website of mine as with other systems, I've discovered that password as well. So that's a problem of storing a password in the clear in the database. And similar, some attacker somehow manages to get access to this database. If the passwords are stored in the clear, they now have the passwords of many users and can use that to access other systems, because many people reuse their passwords across different websites, across different systems. So let's not store the password. So if that is the password, we may store the first thing. Let's store an encrypted form of that password. Let's use DES to encrypt the password, and instead of storing the password, take DES or any other cipher, take the password, some key, and encrypt ABC and store the ciphertext in the database. That prevents the problem. If someone gets access to the database, they'll see the ciphertext, but they cannot see the password. And we encrypt everyone's password. So instead of storing the password, store the ciphertext of that password. What's the problem? Okay. What value of key K do we use? Because we want this to be automatic. That is, we don't want the human user to have to do the DES encryption. We want the computer software to do it for us. We need to store the key K somewhere. So we store that on the file system also. We store the value K. Well, again, if an attacker can get access to the database and we store the value of K in the database, then they can decrypt the ciphertext. So the problem here is that if we rely on some secret key K, to make this automatic, we need to store that somewhere on the system. If the attacker can get access to the system, then they can get access to the key K, and therefore they can decrypt the ciphertext and get your original password. So, what can we do? Use a hash instead of encryption. The same as a MAC or a symmetric key encryption or public key encryption, we need some secret value. But we need to store that secret value somewhere, and if someone gets access to that secret value, then it's no longer, the content can be decrypted. So that's the problem. So the hash, instead of storing the password, we store a hash of the password. Store a hash of the password. We don't need a key for this to work. And we know from the properties of the hash function is that we store this hash value, h1, h2, h3. So now the hash values are stored in the database. If an attacker gets access to the database, they see the hash values. The one-way property of the hash function means it should be hard for them, given the hash value, find the original password. So that makes it difficult for the attacker to find what the original password is and discover your password. So now when a user wants to access the system, they submit their username and password. In the database is the set of usernames and the hash values of the passwords, not the passwords. This is not stored in the database. You supply, user 1 supplies their password. They send it to the system. What the system does is takes the username, takes the supplied password, calculates the hash, user 1 and the hash of the supplied password, looks up user 1, takes the hash value h1, compares to the hash of the password supplied. If they match, assumes the user is authenticated. If not, not authenticated. Because, again, properties of the hash is that hash the same value, you should get the same hash value as the output. And hash a different value and you should get a different value as the output. That is, the hash of ABC should not match the hash of John. That's another property of our hash functions. The hash of two different messages should give two different hash values. No collisions. But of course, in practice we have collisions. In theory we have collisions. So that's the basic way to store passwords in operating systems, in databases, in any computer system that stores passwords. Store the hash of the password, don't store the password. Consider this problem. I'm the database administrator for this website. So I can see everything in the database because I've created the website. But still, I shouldn't be able to see your passwords. Because of this problem, if you reuse your password on my website and you reuse it on other websites, if I can see your password, then I can learn your password for other websites potentially. The set of passwords people use is sometimes, it may be that two people choose the same password. Actually, instead of user 4, let's say it's me, who also has access to this database. And I've used the same password. I didn't know what the password of user 3 was, but by chance, because this is a database about the CSS322 course, I've chosen the password CSS322, as has user 3, just by chance. We choose the same password, same hash value. Now, what the problem here is that if I get access to this, I have access to this database, I see my hash value is h3. I see some other user, user 3, has the same hash value, h3. I know my password, therefore I now know user 3's password. So this is a basic problem that if two users use the same password, if we just store the hash value, then we'll see two hash values the same in the database. And it's a special case where a user that has access to the database could see and discover someone else's password. It's the same as theirs. We'll see how to overcome that in a moment. Let's see how we overcome it now, because then we'll have a quick example. Instead of storing the hash of the password, have some other value, a salt in our database, some other column, some random number. The system chooses this random number called a salt. Instead of hashing just the password, hash the password concatenated with the salt. The salt is stored in the database, everyone can see that. Hash the password concatenated with a number, the salt. And therefore, even if you have the same password, because the salt is chosen as a random number, you'll have a different salt, you'll get a different hash value. Two users with the same password will have different salts, therefore the hash value will be different. The salt is stored in the database. When the user supplies their username and password, we don't calculate the hash of the password, we take the hash of the supplied password and the salt for user 1, which is 347. We get some hash value, and that should match H1 here. So we can use the salt in that way. There's other reasons why the salt is used as well. Let's finish with a quick example, and next week we'll explain those other reasons. A quick example, on a Unix system, this information is stored in a particular file. That is, there's not a database, it's just a text file that stores these values, the username and the hash of the passwords. Let's look at it for my computer. To look at it, I need to be the administrator user. And it's just a file on the operating system in the etc directory called shadow. I need a password to actually look at this file. Looks complex, but let's focus on just the sum of the parts at the bottom. Actually, every line corresponds to a user. Let's look at just one line, and then later we'll see some other users on the system and look at their information. Actually, we'll look at just one of theirs to explain. So to focus on one of them, I'll look at one particular user. Spelled correct? So this is just the entry for one particular user. And the format is defined where we have the username, we have fields separated by colons, the username, then this long string up to here is three things, in fact. We see separated by $signs, we have the value 6, then this value of Z5 up to SX, and then this long value up to R0 at the end. Three things there. The 6 identifies the algorithm we're using, the hash algorithm. What algorithm do we use to perform the hash? 6 just identifies one of the algorithms, and it turns out it's SHA-5112. So it's the SHA hash algorithm used there. The next value, Z5VYE5SX, is the salt. It's stored in the database there. So that's the salt value. It's a random value chosen by the operating system when you create your password. Stored there. And BWW all the way up to R0, the next colon, is the hash value. So what's happened when this user created their account, they chose a password, typed in the password, usually type it in twice to make sure you don't make a spelling mistake. And then the system took their password, created a random salt, combined the two together, applied the SHA algorithm to calculate the hash value, stores the SHA algorithm identifier, the salt, and the hash value in the file here. When this user wants to log on to the system, they supply their username and password. The system takes the supplied username and password, the supplied password, looks up the salt value from this file, concatenates with the supplied password, applies the SHA algorithm, gets a hash value. If it matches this BWW value, then the user gets access to the system. So that's a simple way, or a simple but common way that passwords are stored, in this case on a Linux operating system. The remaining values are just information about the user account, like how long before they need to re-enter a new password, and so on. The salt has another important security benefit. The problem with some hash algorithms, in the past, instead of using SHA, if MD5 was used, where the hash value was shorter, it was possible to generate many known hash values of potential passwords, pre-calculate many hash values, and compare those pre-calculated values against values in files like this. And if I know a pre-calculated value, I know the password I love CSS322 matches some hash value because I calculated that in the past. Then if I see that this hash value matches a pre-calculated one, I've immediately discovered their password. So store pre-calculated values in some database is a way to discover passwords given the hash value using things like rainbow tables. The salt makes such an attack harder. Let's finish there.